In episode 71, titled Injection Families, SQL, Command, Template, we're framing injection as a single core idea with multiple flavors. Untrusted input becomes an unintended instruction. Web apps, APIs, and back-end services all process user-controlled data, and they often pass that data into other interpreters, such as databases, operating systems, or server-side rendering engines. When the boundary between data and instruction is weak, an attacker can smuggle meaning into what should have been plain text. That is injection in its simplest form, and it explains why these issues can lead to anything from data exposure to full system control depending on where the interpreter sits and what privileges it has. The exam wants you to recognize the family quickly, reason about likely impact, and choose safe confirmation steps rather than jumping into destructive testing. This episode builds the mental model you need, what each family is, what clues suggest it, and how to validate and report it responsibly. If you can keep the data versus instruction boundary in mind, injection questions become much easier to decode.
SQL injection is easiest to understand as input changing database queries and results. The application expects user input to be a value, such as a search term or an identifier, and it uses that value to build or parameterize a database query. When the application mistakenly mixes input into the query structure, the input can influence how the database interprets the query, potentially altering conditions, expanding results, or triggering errors that reveal internal details. The risk is not limited to dump the database, because even small query manipulation can expose sensitive records, bypass authentication logic, or alter application behavior in ways that lead to account takeover. A useful exam-level clue is that SQL injection happens at the data layer, so symptoms often involve changes in query results, unusual filtering behavior, or database-flavored error messages. Another clue is that the vulnerability tends to appear where the app builds dynamic queries, such as search features, filters, sort parameters, and reporting endpoints. The practical mindset is that the database is the interpreter, and your input is being interpreted as part of the query language, rather than as a plain value.
Command injection is similar in concept, but more direct in consequence. Input triggers operating system commands to run. This happens when an application takes user-controlled input and passes it into a shell or command execution function, often as part of convenience features like file conversions, network diagnostics, or system integrations. If the input is not properly separated from the command structure, an attacker can cause additional commands to execute, or can alter the command's arguments in ways that change what the system does. The impact can be severe because operating system commands run with the privileges of the application process, which may be high if the service is misconfigured. Command injection often presents as the app does something that looks like a system action, such as running a ping, generating a file, invoking a converter, or interacting with the file system. Symptoms can include strange output, unexpected side effects, or response timing changes if command execution is being influenced. The interpreter here is the operating system or shell environment, and injection is the attacker making it execute unintended instructions. Template injection is a third family that often surprises people because it happens inside server rendering logic rather than in a database or shell. Many applications use templates to generate HTML, emails, or documents, and templates often support expressions, logic, and variable substitution. If user-controlled input is inserted into a template in a way that allows evaluation rather than simple display, the input can be executed within the template engine's logic. The result can range from data exposure inside the application context to broader code execution depending on what the template engine can access. Template injection is tricky because it may not look like classic injection at first. It can appear as odd rendering behavior, unexpected evaluation of characters, or output that indicates expressions were interpreted. It often shows up in features that generate dynamic content, such as email templates, reports, document generation, and pages that render user-provided content with formatting. The interpreter is the template engine, and the boundary failure is allowing user data to become template code. Clue patterns help you decide which family is likely before you attempt confirmation, and they tend to cluster into error messages, strange output, delays, and unexpected behavior. Error messages are a classic clue because different interpreters produce different error styles, and an error can reveal whether the app is failing in a database query, a shell execution, or a template render. Strange output can indicate that the app is returning content generated by an interpreter that processed your input as logic rather than as text. Delays can be a clue when an input influences execution flow, such as causing a query to run differently or causing a command to take longer, though delays can also be caused by normal performance variability, so you treat them cautiously. Unexpected behavior is the broad clue category, such as search results changing in ways that do not match the input, or a parameter causing side effects that feel like the system executed something. The key is to treat clues as signals, not as proof, and to use them to pick the safest next test. When you learn to read these clues, you waste less time on false leads, and you reduce the need for aggressive testing. Impact differences matter because the exam often asks you to reason about what a vulnerability could lead to, not just to name it. SQL injection tends to map strongly to data theft, unauthorized record access, and in some designs even account takeover when authentication checks rely on database queries that can be manipulated. Command injection tends to map to system control and broader compromise because operating system execution can enable file access, process manipulation, and outbound connectivity from the server's context. Template injection sits between those in many cases because it can expose application data and sometimes lead to code execution, depending on engine capabilities and environment configuration. Service disruption is also a possible outcome across all families because malformed input can cause errors, heavy queries, or execution paths that consume resources. The important exam skill is to match impact to interpreter and privilege. A database query interpreter with broad access leads to broad data risk, while an operating system interpreter with high privileges leads to host-level control risk. When you reason this way, your answers become consistent rather than memorized. Safe confirmation thinking is about choosing the smallest test that shows control of interpretation, because your goal is to demonstrate the boundary failure without destructive payloads. The smallest test is typically one that differentiates between input treated as data and input treated as instruction, using minimal attempts and avoiding anything that writes data, deletes files, or consumes heavy resources. For SQL, this often means observing whether carefully crafted input changes result patterns or produces a consistent interpreter-style error rather than random application errors. For command contexts, it means confirming whether input affects execution behavior or output in a way consistent with command parsing, while avoiding commands that would modify the environment. For templates, it means observing whether template-like expressions are evaluated or treated as literal text, again, without pushing into deeper execution. The principle is that proof should be reversible and low impact, and you stop once the interpretation boundary is shown. That is how you remain professional and safe, especially on production systems. Now, consider a scenario where search input changes results oddly, which is a classic way SQL injection risk surfaces. Imagine a search feature returns normal results for simple terms, but when you include certain characters or structures, the results expand dramatically, collapse unexpectedly, or produce an error that suggests query parsing. The clue is that the behavior changes are more consistent with query logic manipulation than with ordinary search matching,
because the application appears to interpret your input as affecting filtering rules rather than as just text. In that situation, it is reasonable to infer SQL risk because search features often translate user input into database queries with dynamic conditions. The safest next step is to confirm whether the behavior is consistent and repeatable under controlled inputs, and whether the error patterns align with database query handling rather than generic application failures.
You also consider alternative explanations, such as search syntax features or encoding handling, because some search systems support operators intentionally.
The point is to treat the odd behavior as a hypothesis and then validate it with minimal, controlled checks that clarify how the interpreter is reacting. A second scenario involves a parameter affecting system behavior in a way that suggests command execution, which is where command injection risk becomes plausible. Imagine an application has a feature that checks connectivity, generates a report, or processes a file, and a user-controlled parameter appears to influence what happens at the system level, such as triggering unexpected delays, returning system-like error output, or changing a generated file's characteristics in a way that reflects command arguments. The clue is that the application seems to be acting like it is invoking underlying tools or utilities based on the parameter, which implies a path from input to shell or system execution. The safest inference is that the parameter may be passed into a command context and therefore needs careful validation of how input is handled and whether separators are sanitized. Your confirmation approach stays controlled. You aim to prove the parsing boundary exists without causing side effects that could disrupt the host or the service. If you can show that the parameter affects command interpretation, you have enough to justify remediation without pushing into damaging execution. This is where professional restraint matters most, because command injection tests can become destructive quickly if handled carelessly. Pitfalls include confusing encoding issues with injection and over-testing destructively, both of which can waste time and create operational risk. Encoding and escaping problems can cause errors and strange output that mimic injection, but the root cause may be input handling bugs that do not allow instruction control. If you assume injection too quickly, you may misreport the issue and lose credibility when defenders explain the intended syntax or encoding edge case. Over-testing is the other danger, especially in command and template contexts, because aggressive payloads can modify state, create files, trigger heavy computation, or disrupt service availability. A professional approach uses minimal, reversible checks and stops when a boundary failure is demonstrated, rather than chasing maximum impact proof. Another pitfall is tunnel vision, where you assume every strange output must be SQL, when the interpreter could be a template engine or another query language entirely. The remedy is disciplined classification. Identify which interpreter is likely involved based on the feature and the symptoms, then validate that hypothesis safely.
Remediation concepts across injection families share a common theme: separation, where user input is treated as data and never as code. Input validation helps by rejecting obviously invalid structures and limiting unexpected characters, but validation alone is not sufficient if you still concatenate input into executable contexts. Parameterization is the core defense for SQL because it keeps query structure separate from values, preventing input from altering the query language. For command execution, safe design often involves avoiding shell invocation entirely, using safe APIs, and strictly controlling allowed arguments if command execution is necessary. Least privilege matters because it limits impact if an injection occurs, such as restricting database accounts to minimal permissions and restricting service accounts from running with excessive system privileges. Output encoding and safe template handling matter for template engines, ensuring user input is treated as plain text and not evaluated as expressions. The exam-friendly summary is that injection is a boundary failure, so remediation strengthens the boundary rather than trying to detect every possible payload. Reporting language should show the affected input, the observed behavior, and the likely impact in a way that is clear and responsible. You identify which input location is involved, such as a search parameter, a header, a form field, or a rendering template field, because remediation depends on knowing where the boundary is broken. You describe the behavior that indicates unintended interpretation, such as consistent result manipulation, interpreter-style errors, or evaluation-like output, without including harmful payload details. You explain likely impact based on the interpreter and privilege context, such as unauthorized data access for SQL, system-level risk for command contexts, or application logic exposure for template contexts. You recommend concrete controls, such as parameterization, save command execution patterns, strict validation, and least privilege configurations. Clear reporting also emphasizes safe validation, showing that you proved the boundary failure with minimal risk and without causing disruption. This makes the finding easier to act on and harder to dismiss.
To keep the families straight, use this memory anchor. Query, command, template all need separation. Query reminds you that SQL injection is about influencing database queries and therefore needs parameterization and strict query construction. Command reminds you that command injection is about influencing operating system execution and therefore needs safe execution patterns and strict argument controls. Template reminds you that template injection is about expression evaluation inside rendering engines and therefore needs safe template handling and output encoding. All need separation reminds you that the core defense is keeping untrusted input as data, never allowing it to become executable instructions. This anchor helps you classify quickly under exam pressure and keeps remediation logic consistent. It also helps you explain impact without guessing, because interpreter plus privilege drives outcome. To conclude episode 71, titled Injection Families, SQL/Command/Template, remember that injection is a data versus instruction failure that can appear in databases, operating systems, and rendering engines, depending on where input is interpreted. Clues like strange output, consistent errors, and unexpected behavior guide your hypothesis, and safe confirmation uses the smallest test that demonstrates control of interpretation without destructive payloads. Classification becomes easier when you ask, which interpreter is being influenced here? A query engine, a shell, or a template renderer? Now, classify one example into the right family as practice. If a search parameter alters database query results in a way that suggests filtering logic is being manipulated, that belongs in the SQL injection family. That single classification habit, grounded in the interpreter, will help you answer exam questions and plan real validation safely.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.